It's me again, the second time, part 2. So I show you how to build a quantum computer. And I promise this time it will be also simple, but appropriate. So of course, it's not the easy topic. And it's always the same. If I stand in a presentation or make one, I'm always super nervous. So yeah, but I will make it, I guess. So yeah, episode 2. Welcome to this. And my table of contents again, I will recap everything we had last time, that the one or someone who wasn't participating last time can also understand what we're talking about. And I think it's really needed to to get again to the topic. And then I will show you for 10 minutes around for the hardware and conditions, like what conditions we need to have for a quantum computer or which hardware will be used. I don't dive too deep because it's quite complex. I could talk here for 4 hours. And I also will switch my seat to the viewer position because I need to rethink how I explain this stuff, because I know everything I talk about, but I need to ask myself, okay, I see a picture. What could I see? And or what you are seeing, and I need to see, okay, what could be your questions while I explain. Then I show you a 5-layer cake that might be tasty, but it's not, I promise. It's like, yeah, you will see later. Then the current barriers of the quantum computing, particular in the machine itself, and later in the global research. And DIY, do it yourself. We want to build our own quantum computer in theory, but actually it's doable. So if you have a bit money, we can make a crowdfunding. So no worries, we'll make it. And the conclusion, as always, I need to summarize the stuff. And I hope there will be no questions, of course, because that's what I can't prepare of 3 minutes. And I try to make everything in 45 minutes because last time I planned for 50 minutes and then it was 70 minutes. Yeah, so time management is on point, but this time I will do better. So let's recap quantum computing. So what is quantum? Quantum is the smallest unit. So you have, for instance, 2 atoms and you have 1 electron that sits on both at the same time simultaneously. So that it sits on the same time at 2 atoms is described by only one thing in the whole world. It's quantum theory. So there's nothing else that will describe it. And this glue that it sits on both atoms, 1 electron, is called the superposition. So remember, we had the superposition, and it's really important that we know that the electron sits on both atoms at the same time. So this is shown here. So we have 2 atoms. I have my laser pointer here. 2 atoms. We have 1 electron, and it sits on both at the same time. So it will make a bond. It's like you have a molecule. And why is it sticking together or be everywhere at the same time? This is quantum theory, called superposition, as I mentioned. And next we will see what we use superposition for. All the behavior in nature, like for instance photosynthesis, is only makes use of the superposition, because if you have a sun, light, like photons, and you have leaves, then with the photons you will get a chemical process, and this chemical process makes a bond and makes oxygen. 2 oxygen atoms will get an oxygen molecule. And this glue, why this could happen, is the superposition. And also, what is a quantum problem? We know that a quantum is a little particle, for instance, just single. It means also single, so the smallest unit. And in normal classical computer, we code information 1 or 0. But in quantum computing, we try to code in superposition, so in 1 and 0 at the same time. That's really cool because we can use it for really large problems, and our classical computers really ill machine for quantum problems. That's why we need to extend it. And let's see, you're sick, or you're sick, you want to recover, then you take a pill. But how do you know that you will recover? It's just in development, it's just try and error. Because if you take in drug development a disease, you just make a lot portions and try what will help or what couldn't help, or you have laboratory rats or animals or everything what you need for, and try what could help. So it's not predictable. And that's really a problem, because we can't simulate the stuff in biological systems, in drug development, for instance. And our current method is try and error. That costs a lot. And I mean, COVID is the best example for this. We don't know really what is happening. We just do it and take it and trust. And that's not good. So with this, we need to know, we know what we can use quantum computer for, but last time we talked a lot about theory, but this time we want to go closer in the hardware and the condition. How is a machine working? We can code superpositions on. Therefore, we focus on the big players like Google, IBM, and Intel. We need to know what is superconducting. So I suppose not everybody knows what is superconducting. So I will explain it. It's if you have microwave or electric low frequency electric signals on a metal or in an electric circle, you will get superconducting. Like it's super cool and low temperature. It's coded in outer space. This is really the method or the current, the method or the behavior that is used for the big quantum computers. Also important is that we don't have a full quantum computing system. So we talk always quantum computers, we want to build one, but it's never fulfilled. It can be extended and extended. So we are now like in the 1980s of the computers. We think we have already a function system, but it's not true. We need to do a lot error corrections and more qubits, for instance, for calculation. Then semiconducting. This is if we use metals like selenium or germanium. And there we make a use, this is selenium, this is germanium. Germanium is super toxic, so just a few amount of this will make you super sick. So be careful. And we use microwave and magnetic field to make a semiconducting circuit. And said Google, IBM, and Intel is using it. Why they're using this? Because from the history, they always used it. So why should they change? But there's even another way to do it. I show you later. We are going to build our own quantum computer with other method or other way, and they just don't use it because they don't have the experience in this, or not too much. So they will stick on what they can. So now we see something that could be interesting. So this is the IBM quantum computer, and you see this white box container. This is actually a refrigerator, a big refrigerator that is our fridge. That is super cool. It's cooler than outer space. Oops. And there's where the whole magic is happening inside. Then you see here, this is the code, the software, what is running on the machine, and all these are coaxial cables that transfer signals, electronic signals inside this vacuum chamber. And this outside, these are all commercial parts. So this is nothing that was really developed for quantum computing. It all already exists. And inside, as I said, it's around 20 microkelvin or millikelvin. So it's in the base, it's really cool. and we need it to have the machine working. I will explain you why it needs to be that cool. But you need to know that the quantum state we had in classical computer 0 and 1 that is perfectly working perfectly well in room temperature, but the quantum state will collapse when it reacts with the environment it's living in. So if you make it super cool, then it can't react with the outer world. And that's why the quantum state can still survive, but later more. And here, this is the system we see here. I will explain a bit more. The quantum code we write, for instance, in Python, there is an open source already existing. It's called Qiskit. I showed you last time, I guess. Yeah, we coded on it. And you can already start coding quantum code. What you actually do here in this layer is to make all the software ready, or the algorithm that will control the electric devices, like to send microwave signals or electrical signals. So that can be done in normal classical software engineering. And with this, you say, okay, this electric signal, this classical computer algorithm will send which signals should be burst into the quantum gates. And this is the quantum chip that exists of quantum gates. Quantum gates are just logical gates that have like what setup you want to make. Why should the qubit be in this position, or what you want to actually code or compute, I mean. You need to make the setup for the qubits itself with the logical register also. So this is the chip. I will also explain it later, so we can just leave it out. Just for you to know in a not too deep, is that we have classical computer code that is sending signals to manage the chip or the qubit. So we need to adjust it and to make a setup. And we can't just write superposition, so we need to have something we know. This is the code we have. Then in the quantum computer itself, this is the electronic devices, like we have a waveform generator. Then we need to say, okay, we need to transform our compiled code into instructions. So we will send microwaves that will affect the qubit. What should the qubit do? And this is all analog, so there's no digital. Digital is happening before the analog signal. So it instructs the signal, okay, you need to do this with this qubit. Then we get the information out. If we measure the state, what is the outcome of our quantum computation? We will get also analog signals back that will be, if we have one error correction would be nice, that we don't have errors, will be transferred back in digital signals and compiled back to our conventional computers. So we can actually read the signals, what is the outcome from a quantum state. I hope you understand everything. If not, no worries. We will come to the better part later. So it's just, we want to know how the actual system is working. And I really tried to break it down, but it's not easy. And the scientific articles are quite harsh and really hard to understand. But yeah, I hope I will make it. So in a normal computer, we have a dynamic RAM. You know it. It's a RAM. We have a CPU and a RAM. What is happening? If we want to have a logical one, our transistor has a capacitor that has electron charges. So if it's filled with electrons, it's a logical one. If it's not and empty, no electrons are in the capacitor, then it's a logical 0. And the normal transistor has around, or capacitor, difficult word, have around 300,000 electrons. This is in room temperature. This is a normal DRAM in classical computers. What we actually try in quantum computing is to have one single electron. Remember, quantum is just one. It's not 300,000 electron, it's one. But what is happening if we have one electron in a room temperature? It will actually try to escape. It leaks out. What is happening if we have a logical one with one charge, with the state one, and it escapes? It will turn to a zero. So our whole computation will get the error. So this is not working in the quantum computing, in room temperature and quantum computing. But in classical computer, it's working because we make a redundancy. We say we make 300,000 in it. So if one leaks out, we can still have the state one because it's charged. So, and also DRAM always checks if it's leaking out electrons, we will put some more in. So it will get more. That's always under voltage. Okay, so now the problem is what I said, if we have room temperatures, we have photons like atoms. Photons are atoms. It's a light particle for those who don't know what is a photon. And photons are electron killers. So if they get in touch with it, they will just grab the electron and say, hey, you're mine, come with me. That's why it's not working. And also why errors appears. And in a normal room temperature, we have normal metal. You see there will happening something with it will react with it, and then you will get errors. But if we cool it down with a superconductor, as I said, they're all around outer space temperature, then the metal will behave different. So the electron can be trapped in the metal, and it's enough to have one electron to make the calculation. The one electron with charge is a logical one. It will be transferred and will still remain in the trap. That's why it's working. And it's really important that you understand it. If you remember here that if you cool down metal like selenium or germanium, you can keep electrons inside or one electron inside and it's not leaking out. If you remember this for today, I'm really happy and I can go later and yeah, have a smile on my face in the train. So then next, CPU. Oh my God, the next one. What is this? CPU. So, and we have a GPU. Quantum power unit is QPU. I said it wrong, I guess. And this is actually what is happening. In a classical computer, you have a DRAM, a RAM, like the short storage of information. And if you want to compute something, you send from the RAM the information to the CPU. The CPU computes it, get a result, and send it back to the RAM, and it will be displayed for you. So it's a symbiose. It's working together. The problem in quantum computing is that if you can't have a RAM, because if you have the qubits and you, let's say, put something in, a signal in, then the whole qubit states will change because you let's say it's a box, you watch into it, some light is coming in, and the light will affect the qubits. You can imagine like this. And then the quantum states will change totally. So you can only check it in the final state. So if you want to have the solution, you can look into it, okay, what is the outcome, but not before. And that's the problem in RAM, because RAM will always check back with the CPU, but you can't check back because you will collapse the quantum state. So it's not working. So the control signals need to wait. And this is really a tough topic. Researchers all over the world are working into to try. Imagine you need to control or make error corrections in the actual computing, but you can't send the signals. How should you do it? And that's what a lot of researchers are working on, that you can affect it without looking into it. I know it's weird, but yeah, I hope you can understand a bit of it. So we have no RAM in a quantum power unit. This is all in one. So let's say the CPU and RAM is together the QPU. And this is actually how our quantum power unit looks like. It's a 2D one. Can also be 3D, but we make a 3D later with the other system. But here in this circuit, it's electronic circuit. It has the RAM and the CPU in one because there's no existing RAM, so it's all in one. There's just the QPU. So now it's getting tasty. We have the 5-layer cake. As always, we start with the cherries on top. So I start to eat here. At the application layer itself, it's important. The application layer is all the software we have. So we write the code, the instruction code, for instance, Python with Qiskit, and say, okay, our algorithm tries to solve a problem, but we need to instruct the quantum computer what should it do, what code is doing, actually, also if you program. And also important is that the application layer is not referring to the layers below, because you should always be able to change the application layer. And that's why it is, you see here the white line. This is the quantum computer. And this one was the little computer I showed you in the picture before that was standing outside of the quantum computer. So this is not 0 Kelvin code because it's a normal computer. And after below this, you have a classical processing. What this is actually doing, it's compiling the electronical devices like the microwave generators and telling them what you need to do and what they need to do. So you need to say, okay, you send like 6 gigahertz to this qubit, and then the qubit will flip in a position that you wanted to have. So really the hard thing is that you need to code stuff that should actually behave in a quantum computer like it should be. So it's like you try to code something, you expect the outcome, but it's not always happening, of course, because this quantum computer has a lot of errors yet. And it's compiling and optimizing the digital layer. Digital processing is like with micro instructions. You actually say what should the electric devices do. And as I said, calibration and tuning, like here's a lot error correction happening. And the measurement is the outcome. So I will go from here to here. And beneath it, you have the digital processing layer. This is inside a quantum computer because I said we don't have RAM and a CPU. In a quantum computer, we have the GPU. And the GPU exists with all these 3 layers: digital processing, analog processing, and quantum processing. This one is saying, this is also outer space here already. This is super cool here. This is saying what should be the microwave generator do actually. Then it sends the control signals, and here actually will happen. Here you will get the 6 gigahertz frequency, for instance. And this is actually sending out and send the analog signal to the quantum bit, to the qubit. And the qubits are processing it. You don't reveal it. You just make the computation. Then you get the outcome in signals back in gigahertz in frequency. And you transfer it in a digital signal. And from a digital signal, you give it back to like polish the signal to say, okay, what could it be in code again, optimize it and measure it. And then this will get you the result on your classical computer like my laptop here. So I hope it's quite some difficult layers. It's not easy to understand because the target is that now this is not working together. This is not all on one chip. There are different machines. This is a machine. This is a lot tuning stuff. This is like a beamer, a frequency beamer. And the target for the future is that we have all these 3 layers in one single chip. And you can imagine a chip is super small, that is super complicated. Nevertheless, it's really it's a diagram that is the lead for all quantum computing achievements so far. So there are 5 different types, and all follow this, more or less. Then you have here something. Now I want to go in this layer a bit more deeper. Imagine you have like normally now you have 10 or 50 qubits, and you want to address them all with analog signals. Let's say we give this qubit 5 gigahertz, this qubit 6 gigahertz, but the range of frequency is limited, so you can't send like million different signals at once. What now is happening here, you can do, it's called multiplexing. Multiplexing is this. Multiplexing, a complicated word. Easily, it's like you bundle signals together. And you group also qubits. Let's say you have 1 million qubits. You don't send 1 million signals. What you do, you group the qubits together. So you make groups, like you make 1,000 groups of 100 qubits. Should be 1 million if I calculate correctly. And then you say, I send 6 gigahertz to group 1 with 100 qubits. And in the group itself, have different signals, frequencies. So then you have a less high bandwidth because you send on groups and not in singular qubits. And this is what is also a part of error correcting, that we can have that many qubits. And the whole thing here is called multiplexing. I just want to take it up as an example because you always see complicated words, but if you translate this, you see, okay, it's bundling together. Okay, we summarize something. Summarizing of signals is a key to make a large-scale quantum computer. Okay, so current barriers. Okay, specific on a quantum computer itself, it's hard to control the signals. So the qubits are manufactured with some metals and so on and electric circuits, but you can imagine a qubit itself is always different from another one. So the quality is not 100%. One is like 95% factored, one is 100. So that's also one problem. The second one is decoherence. What is decoherence? The word also complicated means that something is affected by its environment. So other influences. For instance, we said a photon can influence an electron, and this is actually also a problem because you have many noise, a lot noise in a quantum computer. You need to protect of. So the solution is a quantum error correction. That's imagine you have 10 qubits, but they all not work perfectly well. What you do is you have a bunch like 1 million qubits that will help to correct the state for the 1 qubit. So for 1 logical qubit, you have around 100 physical qubits to make an error correction. They can compute together the error of the 1 logical qubit. So if you have 10, you want to have 10 logical qubits, you need around 1,000 physical qubits to make error correction. This is avoiding decoherence. Then as the speed in the QPU, you can't be as fast as a quantum computer. So if you want to try to edit something, you're too slow. So as I said, we try to have the 3 layers, analog, digital, and quantum processing together in a QPU. And if the quantum computer gets super fast and get more qubits, it has also a lot data. So it's around, I saw that 1 million qubits would have like 10 petabytes of data per second. We can't handle this data at the moment. So it's too fast, give too much information. And the speed in a QPU is like your GPU in your computer, your graphic power unit. What it does is that it computes parallel. So to handle the speed, you need supercomputers to get the signals done. So the speed is too fast, we can't handle it yet, but just roughly. It's important that you get quality is limited, decoherence is a problem, and the speed. But it's just 3 of many. Then the global problem is the International roadmap for quantum computing. At the moment, everybody's fighting for himself. So I would say it's a bit like computer in 1980 or atomic weapons or space programs. They all work for themselves and they can't or not allowed to transfer information. Knowledge transfer isn't made yet between nations or companies, even companies. I mean, the Google guy wouldn't say IBM, hey, we do this. How about you doing this? No, he gets fired. So it's classified. Everybody's working against each other. There are only few little university programs that really try to transfer the knowledge. And that's also what the US government is making it like it's top secret. So you always, yeah, everybody needs to start somehow by scratch. And let's hope we get also like ESA, the space program, that multiple nations work together one day, probably in 30, 40 years. And not like the NASA is, just national. Okay, now I promise you it's getting less complex. Now it's the fun part starting. You want to build your own system? No problem. You can buy one. The one I told you before starts at $2 million. Wow. Like I need to work many years here. And the one we want to build is around $25,000. So it's not fully working. As I said, a system is never fulfilled. It just starts somewhere, have an output, and have a specific scale to work on. But it's possible to have, with DIY, do-it-yourself, a quantum computer for $25,000 dollar or euros. It's 1-1. So yeah, also euros. Nice, perfect timing. Now we see here that this is what the big players are doing. They work with electric circuit. What we want to build is an ion trap. Oh my God, what is an ion? An ion is a salt that is getting overloaded with electrons. So it has more electron charges. So it's negative charged. This is an ion. It has more electron than protons. And this is relatively easy to make. We will see. So there we have electron circuits, but here we want to see the position of the ion, where it is, to get the information like the quantum state. There's even a more easier approach that costs around, let's say we can make one for 5,000 euros or dollar, but it's hard to make. This is the photon quantum computer. The problem is with a photon, a light particle, is that it's isolated and it can't react with its environment. So to have information, for instance, you have 3 ions and they're in a specific position. If the position is more right or more left, you have a logic. You can have transport information because you know they're in a specific position, and you know if the one is more right from the second photon, then we have this information, you know. And the problem is that photons are not reacting to each other, so you can't move them really, and that's really hard to make it in room temperature in your home. So this is not an option for us, because the interaction is weak with its environment, and also the error correction. If you can't control a photon really in a good manner, then you can't make error correction. So you're always trying to handle this guy, but you can't. So we better stack up some case and say we make an ion trap. Let's start with your ion quantum computer. In your ultra high-tech military-grade laboratory garage, you will start with some ions and an ion trap. What an ion trap is, I will tell you later. You have a vacuum chamber. You need to suck out the whole air. Then you need the laser to change the quantum state, because with laser beams, you can actually put in energy level on the ion to give him information. If this has this energy level or another energy level, then you know, okay, it's a different information. And you need software and a camera for measurement. I don't think you can take a normal camera, more scientific one, but they are out there. Let's start. What is the ion trap? An ion trap is like metal electrodes and a bunch of electrodes, and you try to trap an ion in a specific position. And how you can do this is in a 3D room, or let's say construction we make, or even 2D on a chip. We will do both. You need 200 volt to 6 kilovolts, so it's high voltage. And we don't say caution, danger, we say only work in progress. There's no danger in our project. So you should wear some isolated gloves, but only sometimes, if you want. Our goal is to contain the ions in a specific location, so we can put in information on it and read the information out, so they can't escape. We can even see ions if we make some particle on it. We will see later some ions. Then you know they are there, because normally ions you can't see, but if something is trapped or combined with the ion and be on a specific place, you can see it. And it's floating in the air, that we can see it's not just lazy and laying around, it's doing something. The ion trap, your first store of choice should be eBay or Digitech to buy the components. So get some coupons ready. You probably get from birthday presents. Okay, what we try to build is a linear pole trap. The ion trap in this form is called linear pole because Paul developed this one or exploded. So actually you have plus and minus on some, in a form like this, and you see here an electronic field will appear. What is happening in an electronic field, you can line up your ion, but these are just for showing purpose. These are particles, so we can show them here. You can really see them. So we try to build something like this. You create an electric field, so we can use a 3D printer and make something like this. And here you can see here could be your ions. Then you put voltage on. It's perfectly isolated, so yeah, you shouldn't touch. And here you go. You see, if you have electric field with a 6 kilovolt, it's or 200 volt to 6 kilovolt, it means like moderate to high voltage. You can really see here 8 particles floating in a row, and this row can be used as information because they will move. And if you measure the movement, you can measure information and also transmit information. If you get the same result and the income and outcome, you have the same position, of course. So, okay, this is the 3D approach. Now make it 2D. What you should do, of course, you Google and you read the manual, okay? I don't tell you what is F. Okay, so you can find a lot of books of quantum mechanics, or everything's out there in space, I would say also there, but in the, how we say, the holy internet or web. So go there, you will find everything like I did, and you can dig deep. That's what you can find here. We have the 3D approach we made, you see. There the particles floating in the not magnetic, electric field, important, it's electric field. Voltage is electric field, and if you add power to it, it's a magnetic field, just for information. Or you make it 2D. You set here, for instance, a minus, here minus, and here plus on a circuit like a PCB. And then you can have them floating above the chip. So we try to transform this one we made to this one. Oh boy, I need to create my own chip. Call Intel. They will help you. If you try, they will tell you, oh my God, it will cost around $200 million to develop one chip. We don't do it, or I don't suggest you to do. What you do is you make your own. So you make your own chip. It's possible, really. You use a CNC miller, empty ceramic or ceramic chip carrier that you can buy around for $800. You can get one if it's a good one. It looks like this. It's empty. What we are doing is to say we make a simple PCB design that we saw before. And here in a graphic, you see that the ions particle can float in the mid. So you mill the carrier, chip carrier, in this format. So you will see it like it will look like this. After this, you have a finished one, and this is actually how many small companies make it with milling their own chip. But of course, not with this one, with a more accurate one. But we are low budget. And then you can see under electric field in the circuit, your ion particles will also float above the chip. So we made it happen with 3D and 2D. What you need to do to make it happen is you need a vacuum chamber. You can ask NASA and can tell them you have a space, you have a rocket, you have space, you have a rocket, you can send it out to space. I mean, this is a big vacuum chamber. It will work there, of course, but nope, we can't do this. I suggest to build your own vacuum chamber. And to be honest, this is just a bunch of metal. It's nothing, it's no rocket science itself. So we want to isolate, this is what I meant with decoherence. We want to isolate the particle that they are not reacting to other atoms in the system. If there's no air and no other atoms in there, it can't react with anything. That's why we do it. So we avoid a collision to collapse the quantum state. If it would happen, it's game over. You can't compute anything. You're back to classical computer. And yeah, so we need a vacuum chamber. You can buy one. That's not you need to do by your own. I mean, this would be a lot engineering work, of course. You can buy this one, let's say around used $1,000-$2,000. Then you put your chip in. So this is a big chamber for just a chip, but this is what it needs. Next, you need a laser. You want to give information to the ions. So you need to manage the energy levels, and you do it with laser beams. There are out laser kits. Normally, a industrial laser costs 25K plus, and you can make it by your own if you buy a kit. This is a kit, a laser kit. And you need a camera to measure the outcome. So you need to see which position it moved to. And imagine you can align all the positions where you want them to have and say, okay, if it's like this, it's this information. So you're fully free to manage the quantum computer, but you just need to see what is the outcome. And finally, I mean, I have a lot of people here who are working in software, so this could be covered already. We need the software, and there are all, open source softwares out there. I also saw a lot on GitHub by some really crazy guys, and they mostly use C++ or Python. And you need to control your lasers and opticals you have with Qiskit, for instance, also open source. What is to do if we build our own one? Okay, this is how you would go to build your own ion trap quantum computer. I mean, this is really possible. So I think I hope you realize it. So I'm really happy. When I saw this, I smiled and was super enthusiastic to start. If I see your faces, I think you better don't start, but it's fine for me because I like what I do. So the challenges we have now, if we build this, we need to make it smaller. We can't use particles at all. I mean, it's super inaccurate. We need to make micro nanoparticles. this needs more technology. And we need to manage to address one single ion or particle to give specific information only to this one. Because if you don't hit the right place, or something's going on another one, then you have wrong information transferred or created. And yeah, as if the chain is getting longer, we have 8 particles. Now imagine we have 100 qubits, 100 particles. If the whole chain is moving, that will create a high decoherence, so they will react with each other. So this is also, we need to isolate them more and more. This will be our next task on Jira, for instance, if we want to build one. So we are done. And love when a plan comes together. So I would say, let's do a quantum computing department from Mimacom. How about this? We could start with $25,000 or more and make a bit R&D or not. Yeah. So a lot of information. I hope I'm still in time. It looks a bit I'm out of scope, but yeah, let's see. What's coming next? Okay, oh no, he's continuing. I will be sick on this day. No chance. I will call you. So next, there's one chance. I will let you vote. So you can have another season in quantum computing in detail and teleportation. This will be more technical, but I think after this, not. I don't go more deep. I would do something like more practical, I think. So more coding, or we could start, probably I will build a little circuit or something and show it. This could be something for Christmas days. Or the other one, as some know, I'm really in touch with Azure. So I also think to make something cool, I don't know yet, probably a case study where we can make a bit machine learning to react with Azure together, make it on cloud, and program something together, set up the stuff from beginning, from scratch, like a hands-on lab in Cloud Azure, in Azure Cloud. And yeah, so I will make a vote in this chat later, so you can vote. And that's it from my side. I hope you understood like 10%. I'm really happy. And always thank you very much for your attention.